Our topic for today is solving exponential equations. This is part 1. So, what are exponential equations? Exponential equations are equations in which variables occur as exponents. So, this is our first example. 2 to the power of x equals 8. So, what we're going to do is we're going to solve for x. The rule that you have to remember is that in order for you to solve for the exponent, you must make the bases become the same. On my video entitled Expressing a Number in Exponential Notation, I have taught you how to generate and change a number into an exponential notation. So in this particular case, we're going to express 8 as 2 to the power of 3. So 2 to the power of 3 is 8 because 2 times 2 is 4, times 2 is 8. Now that the bases are the same, when the bases are the same, then you can express the exponents as also equal. Therefore, x is equal to 3. Example number 2. 5 to the power of 2x is equal to 625. Now, we're going to review on how to generate the exponential notation for 625 by using the prime factorization method. So 625 can be divided by 5 because it ends with a 5, so you know that this can be divided by 5. If you divide this by 5, then you get 125. With the same principle, you know that you can divide 125 by 5. When you do that, you're going to get 25. And now 25 will be broken down by 5 times 5. Now we're going to circle all the prime factors. And now you can see that we have used 5 as a factor 4 times in order for us to get 625. And so therefore, the exponential notation for 625 with the same base of 5 right here is 5 to the power of 4. Now that those bases are the same, we can now express their exponents as equal to each other. And then now we will solve for x by dividing both sides by 2. And so for this example, x is equal to 2. Example number 3. 8 to the power of 3x plus 5 equals 4 to the power of 5x minus 1. Please note that both of them are multiples of 2. Therefore, I can express both of them as bases of 2, like this. 2 to the power of 3 is equal to 8, and 2 to the power of 2 is equal to 4. And so I'm now replacing 8 with 2 to the power of 3. And I will replace 4 with 2 to the power of 2. Notice that the bases on both sides of the equation are now the same and the base is just the 2. Because of that, we can already operate on the exponents and solve for x. We will distribute the 3 inside with the 3 here and the 5, making it 9, and then this one is 15. And then we will do the same on the other side. 2 times 5x is 10x. 2 times negative 1 is negative 2. Okay, now we're going to solve for x and we're going to isolate the x. Whichever side you decide to put the x, your answer will be the same as mine. I'm deciding to put the x on the right side. The reason is because I'm looking at this, that's a smaller number. If I move it to the other side, 9, positive 9 will become negative. And I will maintain an x that is positive because this is higher, this is 10x. So if I move this to the other side with the 10x, this side is going to turn to 10x minus 9. So this is going to be 10x minus 9x. Again, if some of you decide to put the 10x with the 9 here, that we are going to arrive at the same answer. All right. Now, that means if I'm choosing the right side to be where the x is, I must remove the negative 2 and move it to the left side with the positive 15. The moment you move this to the other side, the negative 2 turns to positive 2. So this side will look like 15 plus 2. All right. So this now is going to become 17 equals 10x minus 9x is 1x or just x. And so this is our answer. X is equal to 17. Okay, flip your paper for the continuation of our discussion. We are now on example number 4. 3 to the power of x plus 5 equals 9 to the power of 2x plus 1. Again, let's find a way on how we can make their bases the same. Notice that for both sides, left and right, 3 and 9 are all multiples of 3. And I can express 9 as 3 to the power of 2 in order for me to have the same base as this one. What we did was we simply removed the 9 and replaced it with 3 squared, which is the same as 9, and I copied the exponent. Now, like what we did in our previous example, you're going to go ahead and distribute the exponent of 2 inside with the 2x and the positive 1. So once again, because the bases are already the same, you can now just separate their exponents and equate them to each other and solve for x. Okay, so x plus 5 is now here. That's your exponent. And here, 2 times 2x is 4x, and 2 times 1 is positive 2. We're now going to solve for x. Now, whichever side you decide to put the x, again, we will have the same answer. However, in my case, I'm looking at the right side having a greater value for x. This is 4x and this is just 1x. So I'm going to decide to put the x on the right side. Why is that so? If I put the positive 1 to the other side, it turns to negative. And so if I minus 4x minus 1, then I will still have a fast positive x value, which I want to have. Okay, so this negative 1x here or negative x here came from here. So this is positive. If I move it to the other side to join the 4x, it becomes a negative x. And so therefore, I'm going to put all my constants on the left side. So 5 will just be copied down, which is positive 5. And that positive 2 goes to the other side to join the positive 5. And when that happens again, the positive 2 turns to negative 2. Again, guys, these are all shortcuts we're applying. But if you need a lecture on how to solve for your equation, go ahead and click on one of my videos because I've discussed that in my other video. So anyways, we're doing some shortcuts. So once again, the positive 2 goes to the other side and becomes negative 2. So this side will just be 3 equals 4 minus 1 is 3x. All right, so now we're here, and for you to isolate the x, you must remove the 3 by dividing both sides by 3. And so for our example, for this example, the value of x is 1. All right, for this fifth and final example, we have 4 to the power of x equals 9. Okay, so 4 can be expressed as 2 to the power of 2. 9 can be expressed as 3 to the power of 2. Wait, the rule says that the bases must be the same, and in all our examples, that's what we've been doing. However, in this particular case, there is no way that 4 and 9 can be expressed in such a way that their bases are the same, as shown by this one. Okay, so when that happens, this is when we use logarithms. So this example is just a prelude or an introduction to the next part of this discussion, which is about log. But let's go ahead and solve this. In order for us to solve this, we are going to put log of this equals log of 9. All right, so not complicated. All you will have to do is to copy this down and put the word log in the front of it and copy the 9 down, put the log in front of it. Now, there's a rule whenever you're solving for the log that this exponent right here can be moved here in the front, like this. All right, and then we're still going to be solving for x. Okay, so I know you're seeing something for the first time. You have not seen this before, but in solving for the x, this is the same as how we solve for x. In order for me to isolate the x, the log 4 needs to be removed, and that is times right there. So in order for me to remove log 4, I will have to divide both sides by log 4. And so this log 4 over log 4 cancels out and it turns to a 1. And so the left side will just be x. All right, and then log 9 over log 4, you guys, is a decimal. This is a number. So let's use decimals in order for us to get what specific number this is. When you plug in log 9 over log 4, it's going to give you this decimal that is approximately equal to 1.58496. Let's use that. And so now, once again, your x is approximately equal to 1.58496. Now, look how cool this is. Let's do the checking and substitute that x value on the exponent here on x. So 4 to the power of this, and let's see if we will get 9. All right, so using Desmos, the moment I had put 4 to that power of 1.58496, we get a number that is approximately very, very close to 9. And that's all we can do, guys. We can approximate. And this is approximately equal to 9. So this is accurate. So now the checking works. And so once again, for this example, our x is approximately equal to 1.58496, and we got that using the log. So see you in part 2, which is a bunch of examples solving for exponential equations using log.